Ionis for the introduction. So I'm here on behalf of my colleagues from NEC, I2CAT, UC3M, and in the networks to present our work on reliable radio access network virtualization. A special credit here to the first author of the paper, Ginés Garcia, who really did most of the heavy lifting here. Okay, so virtualizing a 4G, 5G base station is an inherently hard problem, right? There is, yeah. It's okay. No, it's okay, thank you. Okay, so virtualizing a 4G 5G station is an inherently hard problem. That's the point here. And as you may know, the pipeline of physical layer tasks that are involved in the physical layer of a distributed unit, has tight and hard deadlines. These deadlines are harder for DUs, for distributed units, than for classical network functions or even for the central unit in a base station, whose quality of experience is somewhat proportional to the latency performance of the computing platform that is, hosting these virtualized network functions. In the case of distributed units, in the case of DUs, violating deadlines imply that users may lose synchronization with the base station, and if this happens, the network will collapse, basically. So violating deadlines in distributed units is more impactful than violating deadlines in classical network functions. So for this reason, the industry today relies on dedicated computing infrastructure. They do this by essentially offloading the most compute-intensive tasks in a distributed unit, which is usually forward error correction coding tasks, into a dedicated hardware accelerator that can perform this task very fast and importantly with deterministic latency performance. And Intel FlexRun, which uses FPGAs, or NVIDIA Aerial, which uses GPUs, are two examples of solutions that the industry is using today. However, using this type of dedicated hardware accelerators is very expensive. What you can see on the screen here are two statements from top executives in the industry, acknowledging that using this approach, using dedicated hardware accelerators, render base stations that are more expensive and more energy consuming than the classical base stations that we've been building for years based on hardware ASICs. So we need to find new solutions to virtualize, to attain the advantages of virtualization without the costs associated with dedicated hardware accelerators. The solution is a bit obvious, right? So what we want here is to share computing infrastructure, to share hardware accelerators. And this is in fact in line with the activities of the Oran Alliance. So in this way, we can actually exploit the computing performance of hardware accelerators at an affordable cost per base station, because the cost is also shared, right? Now, while this is very appealing for the future of virtualized runs, there is an important challenge. Sharing implies non-deterministic computing performance and a distribution of the latency performance that has a very long tail. Task schedulers optimized for this purpose, may help, of course, but they cannot provide 100% guarantees that the deadlines will be satisfied at all times, unless the computing platform is over-dimensioned or dimensioned to the very worst case scenario. And in fact, the standard in the industry, which is using dedicated hardware accelerators, is a way of doing this over-dimensioning. And as I mentioned before, this is very expensive, and this is certainly something that we want to avoid. And in the case of base stations or distributed units particularly, this is a huge problem, because failing to meet deadlines implies that important frames or subframe signals that preserve synchronization with the users will not be sent to the users when they expect them, and therefore they will lose synchronization. So let's analyze in more detail the root of the problem here. So every 1 millisecond, a distributed unit receives OFDM symbols or radio samples from the radio unit, encoding one uplink subframe. This uplink subframe carries control and data channels, including all the data transport blocks and control feedback sent by the users. Processing these channels consists on additional pipelines performing the modulation of OFDM symbols, forward error correction, coding, decoding in this case, which are actually compute intensive, right? However, only once all these channels are processed can we then make scheduling decisions, and not before, because these uplink channels carry information that is needed to calculate scheduling grants, such as feedback from the users about the buffer states, whether they have data to transmit or not, or the quality of their downlink channels. So we cannot do scheduling, calculate scheduling grants before we process uplink channels. And only once we calculate all these scheduling grants both for uplink and downlink, we can then actually process a downlink subframe that includes all the corresponding data and control channels, in addition to other important signals, synchronization signals that preserve synchronization with the users. And then you build this downlink subframe and you send it back, you send it to the radio unit. 3GPP imposes latency constraints between uplink and downlink channels. And for instance, in LTE, users expect feedback of the hybrid ARQ process in exactly 3 milliseconds. In 5G, this latency constraint, you can actually configure it, but it is usually 3 milliseconds or even lower. And this latency constraint essentially implies a hard deadline to process every single job, which is issued every 1 millisecond. I wanted to here actually to mention two very relevant works in the literature. Agora, which was presented at Connect 2020, and actually made it possible to process massive MIMO baseband operations in general purpose CPUs, which is rather impressive for data channels. And Concordia, which was presented at SIGCOM this year, 2021 actually, introduced a task scheduler that prioritized the workload of base stations over the workload of other applications that are sharing the same computing platform. Now, while both of these approaches help certainly and can be used concurrently with the solution that we're proposing here, they alone cannot guarantee 100% that latency constraint will be honored at all times when multiple base stations share a capacity constrained computing platform. So in shared computing platforms, as I mentioned earlier, we do not have deterministic computing latency anymore, right? So it will happen that some tasks, especially those more compute intensive that involve processing data channels in the uplink and downlink directions, as depicted in red in this slide, may occasionally take longer than expected and cause that the whole job violates this deadline, as illustrated here. As a result, a downlink subframe containing all these important control and synchronization signals cannot be delivered to the users when they expect it, and they lose synchronization, as I mentioned before. Now, to illustrate how relevant this problem is, we actually set up a toy experiment. Here we deployed 2 virtualized base stations, and for the aim of this experiment, we used vanilla SRX Run, which, as some of you may know, is an open source LTE stack which implements 3GPP compliance and implements all the layers of the protocol stack of a base station. Now, one base station 1, exchanges as much traffic as possible with an UE, and the y-axis of the plot that you can see on the screen shows its application layer throughput performance. For the second base station 2, we gradually increase its load as indicated by the x-axis of the plot. And as you can see from the yellow curve, at some point, the computing interference generated by this second base station causes that base station 1 misses very important deadlines, and the throughput performance falls to 0 because the user basically loses synchronization. So in this paper, we proposed Nuberu. Nuberu is a redesign of this distributed unit pipeline that I introduced before to make it reliable to compute in latency fluctuations, irrespective of the task scheduler that you use. And as you can see in the slide here, when we repeat exactly the same experiment with Nuberu, we can preserve maximum throughput irrespective of the computing interference generated by the base station 2, right? And here, both Baseline and Nuberu are using the same default Linux scheduler in this case. So how did we achieve this? Now, a simple illustration of Nuberu is shown at the bottom. The underlying idea is extremely simple. So every job, every 1 millisecond, we make sure that in the very worst case, we at least process the most critical tasks, those that preserve user synchronization, and build what we call a minimum viable subframe. Even if to do so, we have to sacrifice data channels somehow. So to this end, we first separate data processing tasks, which are the most heavy in terms of computation, from the main pipeline. And second, we set up a new deadline, which is depicted in blue here in the middle of the pipeline, for these data processing tasks to finish. So in this way, we make sure that Nuberu always has enough residual time for these other critical tasks that enable what we called before a minimum viable subframe with all these critical tasks that need to be delivered to the users. So in a way, the idea is obvious, right? So we are protecting here the most critical tasks for reliability. However, to decouple data processing tasks, we need to break many dependencies that these data channels have with the rest of the pipeline, and this is not so easy. To solve this problem, actually, we integrated or implemented 3 key techniques that are actually based on predictions and congestion control. The first one is what we call a 2-stage downlink scheduling approach. Here, as soon as a job begins, we generate temporary downlink scheduling grants proactively without awaiting feedback from the users that actually are carried by uplink channels that have not yet been processed. And to this end, we rely on predictions based on previous data. This allows us to begin processing downlink transport blocks without having to wait for uplink channels to be processed, right? 2 events may happen. That a transport block or a temporary grant with a transport block finishes before the deadline, the blue deadline depicted on the screen. In that case, in the second stage of the scheduler, of the downlink scheduler, confirms this temporary grant and includes this transport block in the current subframe that we are building here in this job. Or it may happen that a transport block from a temporary grant does not finish its processing before the blue deadline. In this case, what we do is the second stage of the downlink scheduling ignores this temporary grant, right, for this particular job. Then once the transport block is encoded, is processed eventually, we store this transport block, encoded transport block in a buffer, and then the scheduler will actually place this transport block at some other time, some other job in the future, whenever it fits. So in summary, what we do here is we delay the delivery of data to the users temporarily when we experience high computing latencies, just to make sure that the users will at least receive control and synchronization signals in a minimum viable subframe. The second approach is early hybrid ARQ. Once we receive an uplink subframe, we start processing the data transport blocks therein. Like before, 2 events may happen. That a transport block is processed before the blue deadline. In such a case, following the standard, feedback from this process is used by the uplink scheduler to issue new grants, just like the baseline approach does. Or it may happen that a transport block is not decoded in time. In that case, we exploit extrinsic information available from the iterative algorithm implemented by the 4G or 5G decoders to make a prediction about the decodability of this transport block. And then we use this prediction as feedback information for the scheduler to issue new grants, as if this information were the real thing. In a way, what we're doing here is we are softening the time constraints associated with this processing of uplink transport blocks. And in this way, we do not block the generation of a downlink subframe just because we are waiting for processing uplink transport blocks. And the last technique is congestion control, which consists of a very simple feedback control loop inspired by TCP that regulates the size of uplink and downlink grants depending on whether transport blocks are encoded or decoded in time or not. If they are processed in time, The congestion window associated with our controller grows additively because we understand that the computing capacity at this moment is large enough to keep growing the size of the transport blocks. If transport blocks cannot finish in time, we shrink the congestion window because we understand the computing capacity at that moment is not large enough to sustain these large transport blocks. So this allows us to regulate the demand for computing resources to the actual capacity of the platform. I will just add that how much we grow or shrink this congestion window is dictated by a parameter, lambda in this case, which roughly speaking sets the aggressivity of this congestion controller and establishes a point of operation in a trade-off between throughput and delay that I will show later with our results. So to evaluate Nuberu into a full-fledged 3GPP compliant base station stack, what we did is we modified the physical and the MAC layer of SRS Run, which is an open source full stack implementation of an LTE base station, and compare this modified version against the vanilla SRS Run, which implements the baseline approach, which I introduced. Now, I only have time to briefly show a couple of results. Again, took a look at the paper for a more thorough evaluation. We also have a video of a demonstration of Nuberu online, should you be interested. So in the first result, we deploy a base station under test, either the baseline approach or Nuberu, in a computing platform that is shared with a different number of competing base stations that operate at full load. And these plots show the uplink throughput in the left, downlink throughput in the right of this base station under test as a function of the number of competing base stations in the system. The yellow bars that you can see now on the screen display the performance of this baseline approach. And as you can see, as we would expect, its performance collapses as soon as we have competition for competing resources because, you know, deadlines are missed and users get lose synchronization with this base station. These green bars show the performance of Nuberu without enabling early hybrid ARQ. And as you can see, the reliability that we provide with our approach, with our design, allows us to preserve maximum throughput in the downlink direction. And in the uplink, since we do not have activated early hybrid ARQ, the performance degrades only linearly with the number of competing base stations. When we activate early hybrid ARQ, what we can see is that we can sustain almost maximum throughput in the uplink direction as well. In the last, of course, all this reliability comes at a cost, which I haven't really shown it to you. But I wanted to highlight that in this second result and final result. Here we only have one base station with Nuberu or the baseline approach. And what we do is we artificially slow down the speed of the processor that is, processing all the workload of the base station. And how much we slow down the processor is indicated by the x-axis. So if we move on to the right-hand side of the x-axis, we have a slower processor. In the left plot, we saw the throughput performance of the base station. In the right, we saw the data delivery delay, right? Now, again, the yellow curve here shows the performance of the baseline approach. And not surprisingly, at some point, when the speed of the processor is slow enough, all the competing deadlines will be missed, the user will lose synchronization, and throughput will collapse. Now, in contrast, we have Nuberu with different parameters that establish a different point of operation to this throughput versus delay trade-off. So the price to pay here to attain reliability is that we cannot optimize both throughput and delay at the same time during moments of deficit in computing capacity, but in exchange, we do provide 100% reliability guarantees, which is very important and is certainly not achieved by the state-of-the-art approaches. So this is the final thing I wanted to say. I will be happy to take questions.